Okay, so let's talk about Perceptron and continue our discussion about supervised learning algorithm and the example that we had about the credit risk scoring. So in this example, we had what? The response variable that we can identify that as the y with two values, that it could be 0, 1, or -1, 1 as the default and non-default. So this is the situation of the customer that we want to see with the different probabilities of the default of the customers with the different characteristics. If finally we can predict it as a good customer or bad customer, or the loan as the good loan or bad loan, or default or not default. So based on some characteristics that we can have them as the x's, we want to find out about this response variable for y. So this is a kind of binary classification problem that we want to solve it. And what we have in this binary classification problem, we have a vector of x's that can be identified with this x1, x2 till xn. And these x's are what? The inputs of our model. Okay. And then what we had in the middle, function that use all these inputs to make a summation of all the information that we put or ingest the model as our inputs, with some, of course, weights that we can say that beta 1, beta 2, beta 3, and here beta n. So we have either here that is what? A summation of the multiplication of bit betas to x's. But also we can identify here, we can add a bias as the beta 0. So beta null here can be also added to this adder, and these parameters that we have here as the betas can be listed as a vector. And what we need to do to have this adder multiply of these two vectors from x1 to beta 1, x2 to beta 2, and finally to beta n. So this is what we had in the middle, as we could see also before. And then we need threshold activation that traditionally is a kind of step function, so we can define it as a step function, this activation function. To have what? To finally know about our response variable that we are looking for as the value 0, 1, or as we said, -1 and 1 that we have in our list. So it depends that how we define the response variable for our default. Okay, so in this problem that we want to know about the situation of the loan and application that is applied for the loan and for the credit, we have this model with the activation function, with the adder of the whole information that we ingest into model as the input, and also some parameters that they have to be estimated for our model, that our model can work for predicting something for future. So in this part that we reviewed all of this also before, we have this summation here, so we can say that it is something equal to x1 beta 1, x2 beta 2, xn beta n plus the beta null as the intercept. That will help our model to be more realistic if we have an intercept, and it can help the model to have better accuracy, then the intercept should be also considered into our calculation. So this is the summation of the xi beta I plus the beta null. That could be also be written as what? As the beta null plus the beta transpose to the vector x. Okay. So we can have the different values for the response if the beta transpose x plus beta 0 be lower than threshold like 0, and if it is greater than 0, we can consider it as a good loan and with a value of 1. So what we need to have is the activation function here to add the nonlinearity into our model, and this activation function would be something like this. Okay, we will go up to this 0.5 here at the 0. And we have to make the correction in the values, the estimations of the betas of the parameters to have a good output and the highest accuracy for our model. So let's see how we can do it. In this classification problem, what we have is basically some points that we can have them here. Imagine that they are the green points. And we have these red points here. And then we can consider a hyperplane that is in 2 dimensions. So a hyperplane in R2, that is what? That is a line. And what we need to know is that the equation that we had from our model, if we consider it for example, x1 and x2, if they are on this hyperplane, for sure, we will have what? The beta transpose x plus the intercept is equal to 0. So from this, we can include that the beta 0 would be equal to minus beta transpose x 0 for what? For any x0 on hyperplane. Okay, so for any x0 on this hyperplane, we have this conclusion that the beta 0 or beta null is equal to minus beta transpose x 0. And also, from this again, we can have this x1 that is here equal to 0. And for x2 also, it would be 0. So both of them are equal to 0. And we can have this equation. As a result, the beta transpose x1 minus x2 would be 0 because these two beta 0 will be removed from the equation. And the meaning of this means what? It means that the beta is orthogonal to x1 minus x2. Means that we can have this beta as a line here. And the problem that we want to solve is calculating the distances of this axis that we have here to this hyperplane. So this distance is important, and this distance according to this beta that we have here should be calculated to do what? To fit a model or a hyperplane or a line if we are in R2 that have the minimum distance to most of the observations that we have here, or in average to all x's. And it can be in the middle of the red ones and the green ones that can divide these two categories or these two classes in a right way and with the highest accuracy that is possible. So these distances are the measures that will help us to make a model that is the best model, and they can divide the red dots with the green dots in the best way. So we like to know about this and this distance. So the distance that we have here if we consider it as x, similar to what we have here, consider this as also x0. Similar to what we had for the x1 and x2, we can have for x and x0. And it would be equal to what? The beta 0 transpose x minus beta transpose x0. And this beta transpose x0, as we could see here, beta transpose x0 is beta 0 or beta null. So we can put the beta null here and the beta transpose x also here. Okay, so this 0 should not be here. Let me break it. And this transpose is here minus the beta null. Okay, so this is the distance that we can calculate for the x for this observation that we have here, or the axis that we have here, regarding to whatever we wrote before, and this distance that we have here, and we calculate it like this. And this is a signed distance. That can be positive, like the distance that we have for this x, or if we have to calculate the similar thing for one of these green lines, for this one, okay, and this distance in green, so it would be negative. So on the one side of this hyperplane, we have the positive values. On the other side, we have the negative values. And the distances that we calculated can be positive or negative as the signed distance. So this is not a real distance. That should be always positive, and we like to have the positive distances. So how we can make it positive? If you remember, the y, the value of the y was the what? It was +1 or -1. That the positive one could be considered for the red dots, and the negative one can be considered for the green dots with the negative sign. So if we multiply this y for x's, so if we have this beta transpose x1 plus beta 0, for example. So if this is positive, the y, the corresponding y would be also 1, and the multiplication would be positive. If this is negative for the green dots, then y would be -1, and -1 multiplied to a negative value would be again positive value. So it could be considered as the real distance between these values and observations that we have here, with the positive value for the distance, even if it is negative or positive, or in the right side or the left side of this hyperplane. Okay. So this is the distance that can help us to make a good model and calculate the error for our model and try to minimize it, the amount of the error, the total bias that we have in our model, to have a good model and to find the best possible model based on our data. So we have to consider this distance and use it as a measure to optimize our model to be the best model possible. So what we can do to find the best model, we can consider the number of misclassified points. So if I consider that, for example, one green line, green dot is here, and some of reds are considered as the other side of this hyperplane. So if I count the number of misclassified points based on my model, then I can have a measure to understand that which model has the lowest count of these misclassified points, and I can identify it as the best model. So maybe the simplest way is to calculate the number of these misclassified points. So the number of misclassified points might be helpful. To have a measure to compare the different models. But this number of misclassified points is what? Is a discrete measure. And finally, I want to minimize the measure to have a good value or a good index to find the total bias and minimize that total bias. And I have to use some mathematical tools that I have in my toolbox to find the minimum or maximum, right? And to find this, we have what? We have the derivative in our mathematical toolbox to be used to have a minimum or to calculate the minimum of this total bias or these total distances, and to find a good measure for my problem, to compare to different models and choose the best one. But we know that this derivative is not working for discrete measure, and I have to have a continuous function that I can apply the derivatives to find the response. So this number of misclassified points could not be used, but I have this distance here, I calculate it here, and maybe I can use it as a solution. So the distance that we calculated before was equal to theta transpose x plus b 0. And here I had it with the positive sign. Here I add a negative sign. And this negative sign is coming from what? Because this distance is going to show me the error. So basically, it should be related to the points that they are misclassified. So at this point, based on this hyperplane that I have here, the green points are on the side of the positive points, like the red ones. But we know that the green points, they have the negative sign. At the other side, we have the green, the red points. The red points are among the green points are identified as misclassified points. But we already know that based on this hyperplane, these red points, they have the positive sign, but now they are on the other side of the hyperplane. So they are the errors, they are the misclassified points. And the sign is different. So to make this correction, to consider the green ones with the negative and the red ones with the positive, we must add this negative sign here, and this distance can give us the total bias by making a summation of all of these distances. Theta transpose x plus beta naught. So this is what we can expect in the two-dimension problem in R2, but we can also have higher dimensions with, for example, 3 dimensions, right? And in this case, the hyperplane is a plate. Could be considered something like this, okay? With red points here, and with green points. Right? So the hyperplane in R3, as we can see here, is a plate. But with the similar logic that we had here, we can also calculate everything and the total bias for this problem. So what it could help us to do, we are looking for what? if we want to simplify the problem somehow, we have the real target function. That is a function that is working in the real world. That's a stochastic function that is making that problem that we want to solve it. It can be the real output of all the loan applications that they are applying for the loans in a financial institution. And we want to know about this real function. We want to have a kind of estimation for this real target function. This is our goal. We want to know about the parameters of this function and to know about this real function in the real world. That is almost impossible, because the only thing that we can see from this function is what? Is the data. It means that some outputs from this real function in the real world. And if we could see this real function, there is no problem to be solved. We already know about the function. We can use it to know about what might happen in future. But the only information that we have from this stochastic process in the real world is the data that we can observe. So this is the target. We want to know about it. It has a class of functions. We generate what? We generate this data that we consider them as observed data. So this data is the only output that we have from this real target function that we want to know about it. And if we know about it, we might be the God, right? The only person that know about what really might happen in the world is God, and we can only have an estimation, we can only have a forecasting that has an error for sure. We cannot have this function, the exact function that is acting in the real world, but we can have a function, a mathematical solution for that function in a very, very close to what is really happening there. So what I can have is not this real function, but I have a toolbox from mathematics that will give me a class of candidate models that I can consider them as what? As the f, theta, and x. So I can consider, for example, three parameters for this theta m as the theta 1, theta 2, and theta 3. So let's consider only three parameters that I want to estimate to have my model. So this would be theta 1. This could be theta 2. and this would be theta 3. Okay, so the first dimension, the second dimension, and I can consider here also the third dimension. Okay, so for each of these theta, I have to calculate, must have an estimation. Okay, so this could be what? Kind of approximation of what? Of the real data that I had in my target function. And when I making these kind of estimations for the thetas, I will make a bias, right? This is estimation error, okay, that I have for theta 3. I have also the estimation error for theta 2. So I have this distance from my hyperplane to theta 2, okay? They are all orthogonal. So this is the estimation error also, but this one for number 2. And here also I have this distance. So this is the estimation error for theta 1. And finally, from all of these, I can have a total bias. That is distance of my estimated model to the real target function that I have it here. Okay, so we can have a model error. That is the distance that I have from the class of candidate models that might fit to this real target function and the target function that I have it here. Okay, so what I have here as the real target function the fx with the parameters theta m star is projected on the smaller continuous linear space. And why we need this continuous linear space? Because of the derivatives that we want to use. Okay, so the tool that we have from the mathematics to help us to calculate the minimum for the distances needs the function to be continuous, and this is the summary or the graphical summary of what we are doing based on the distances that we have from the hyperplane and the models that we can consider. And these models are all mathematical models, right? So we need to use the tools from the mathematics that we have in our toolbox. So if we consider this model error that we have here, and we call it the loss function, that can help us to calculate the total error that we might make with the candidates for this real function that we want to estimate it. This loss function is important for us to be minimum for the model that we want to use, right? So finding the minimum of this loss function is important to make the model error minimum. and find the best possible model for our problem. So what we can say about this loss function, something that is important for this is calculating the minimum. So let's consider the bias, error, or the loss function, okay? As something like this with the minimum that we are looking for, okay? So for finding the minimum of this function based on the loss function, we can use the gradient descent optimization algorithm, for example, that is works like what? I can start from here, okay, if this is the loss function and I want to find the minimum. I can start from here and then move forward. For each of these, I can calculate the gradient and the slope of this line to see that if it is 0, so I reach to the minimum or not. And the steps that I go forward can direct me to the best minimum in this graph. So these steps are important. And the distance that I go forward in each step is also important. If this distance be maybe a step, very small steps, so I will approach to this minimum in a very long time, and maybe the iterations that I considered for my optimization algorithm could not take me to this minimum because I consider, for example, 10 steps, and finally, after 10 steps, I might be here, not here. If I take the long steps, so it might be like this, and then I will be here, and then I have a positive loss also here, not the minimum one. And then if I want to turn back, I will be also here, and then I will be here, and I could not reach to this minimum that I have. So the gradient descent optimization algorithm tries to have a long distance or long step at first, and then when it approaches to minimum, it decreases the length of the steps, and it will try to not pass the minimum to go to the other side, or to even be trapped in the local minimum and not get to the universe minimum that we might have in our graph. So what we can do is using the gradient descent, okay? The gradient descent algorithm. to find the minimum value by taking the steps from an initial guess that can be here, okay? To reach the best value, so we start from an initial guess and then try to make the good steps and the step lengths to reach to the minimum of that loss function or the bias or the okay. So the learning rate is very important here to be considered. The learning rate might be too low. So we will have very small steps, the baby steps here, and it might take a lot of iterations to reach to the minimum of this loss function. Okay. The better approach for this might be starting from initial value, then with big steps first, and then the smaller steps at the end, so it might be considered as good learning rate. If you have the higher learning rate, what might happen? Might be something like this, so we cannot reach to this minimum, okay? So the learning rate is very important to be considered as a good value. So if we have the epochs here and the loss function here, we use what? The gradient descent optimization algorithm. And we might have this one, okay? Let me change the color with the same color that we had in the graphs. Okay, so this one is the learning rate too high. We can have the good learning rate. So or we can have the low gradient rate, right? So if we have it as the low, it will go gradually to close to the good one, but maybe not exactly the good one. So this is the low gradient rate. So basically, we want to know about the total bias of our model in comparison with the target function that we are looking for. We want to know about the bias error or loss function. And to minimize this loss function, we can use the gradient descent optimization algorithm to do this. And for this gradient descent optimization algorithm, we need to know about the learning rate and the steps that we want to consider here, and the number of the steps that we want our algorithm to use. And that should be a good one that can lead us to the best answer possible for our model.